I am pleased to introduce Professor Joerg Werner. Professor Werner did his PhD at Cornell University and is now an assistant professor here at Boston University in the Mechanical Engineering and Material Science and Engineering departments, where he leads the Mesostructured Materials and Devices Lab studying nano and microstructured functional materials, polymers, coatings, and platforms for self-driving materials discovery. He is the recipient of several honors, including the DARPA Young Faculty Award in 2023. Please join me in welcoming Professor Werner.
All right, I'm going to try to stand up here to talk and use the virtual laser pointer, which doesn't look like you can see it. Let's try that again. There we are. Nope. No laser pointer. Try that again. There we are. All right. So thank you very much for the introduction, and thanks very much for the invitation to speak here today, pretty much on home turf, so I appreciate that. And I have the beautiful view, not like you. You have to look at my slides, but I'll make it worth your while. There'll be some beautiful pictures as well. So I today will talk a little bit about pores and porosities and electrodes on multiple levels. A little bit as a primer, what we work on in my lab is, on the one hand, porous materials, and you'll hear quite a bit of that, especially using phase inversion and maybe a little bit of polymer blends and block copolymers, but it all kind of revolves around making porosity with polymers, and I'll be talking about that. We do quite a bit in electrochemistry or electrodeposition to make ultra-thin coatings, which are often meant for those porous materials. Though we've really gotten into using those as a platform, a chemistry platform that's very modular for self-driving labs to look at polymer materials discovery, and that has pivoted over the last couple of years away a bit from the energy sphere, so I decided not to talk about that today, even though it is, of course, very related to data science and combinations of AI and experimentation. So if you want to talk a little bit about self-driving lab, autonomous materials discovery, I'll be here for the coffee break and we can talk about it then as well. But today I'll be focusing in on these porous electrodes that we use in batteries. Now, before I get started, most of what you'll see today was done by Anton, who graduated from my group last summer, and he was supported by a few students that are underlined here, and Brendan currently, if you have questions, you should definitely talk to him as well, who's taken up that work and continuing it in a variety of directions. Now, I want to start with kind of the basic structure on multiple levels of a battery, and I took this from it might not be referenced here, but it should be somewhere. Honest Energy, there's a really cool online website that I can share later on as well. It might show up again that has a very simplistic explanation of what is all in a battery and what are all the structures that seem to matter, though we don't necessarily know every single detail yet, really what matters and impacts what. We'll get to that later. But anyway, so if you look at a battery, you take it apart, you'll see a lot of layers. Right? And if you zoom in, there's 5 key layers that a battery usually has that you need to pay attention to. So on either side, you have your copper foil and aluminum foil, which are your current collectors. So those are just metal foils that help you extract and input the electricity during discharge and charging, right? At the same time, they also usually hold your material. So the material that really matters, your anode and cathode material that's storing the energy, those are usually powdered materials that are essentially painted on these metal foils together with some polymer binder, often some conductive additive to allow the electrons to get from the foil all the way through this layer and back. And then these paints themselves have porosity through them. And why porosity matters, we'll get to in a second. And then in the center, you have a layer that physically separates the anode and the cathode, because otherwise, if they touch, you just run a chemical reactions or a short circuit. You're not actually running your battery to extract the electricity. So you need to have some kind of electronic insulator to separate your anode and cathode. Now, what's important in a battery, in particular lithium-ion batteries, but really any electrochemical system, is that there's ion transport between them. right? For different chemistry, that looks a little different. For lithium-ion batteries, it's really the lithium ions, hence the name, that shuttle back and forth between your anode and your cathode materials during charging and discharging, right? Now, these lithium ions in your standard batteries go through a liquid. That's called the electrolyte, and that liquid is imbibed in the porosity between these active materials here, which again are usually powders held together by some polymer. So that interstitial particle space is where your liquid goes, and that's where your lithium ions can diffuse or migrate around from one side to the other. And your separator, therefore, is usually also porous, so that liquid imbibes that porous plastic, typically separator as well, so your ions can actually get all the way from one side to the other. Now, the way we typically usually, or do that these days in industrial applications, is we literally just paint this onto the metal foils. We often compress it. So the porosity you have between these particles is very tortuous, pretty small, which is something you often want to have, because the less pores you have, the more material you can put in there, the more energy you can store. At the same time, the less pores you have, the more tortuous there are, the harder for those ions to move back and forth. So when is that ion movement relevant, especially the speed of that ion movement? It's while you're charging and discharging your battery, right? How fast can you run your battery, in the end, is really determined on how quickly can these ions move back and forth between the anode and the cathode. Now, because of that, what we find is this little bit of a conundrum. I call it often the energy and power conundrum. Energy being how much energy you can store in your battery. Think of your EV or your phone. How long does it last, right? Now, ideally, we want a lot of energy in our batteries. So a simple solution would be we look at our 5 layers, right? Let's just increase the fraction of those that store the energy, anode and cathode, right? And they're making thicker. Keep all the others thin, and that way we have in the end 80–90% energy storing material, only 10% or so dead material, which is not currently the case. We're at like 30% or so of these inactive components, depending on if you look at weight or volume, right? Now that is nice, and what I show here is kind of a plot of the power density. Power is energy per time, right? How quickly can you put that energy in? Think of it as a charging time, right? The higher the power, the faster you can charge it. Now in blue here is a very thick electrode, 65 micrometers. In black here is a thin electrode, 35 micrometers. So the blue one on the cell level can store more energy. The y-axis here is on the log scale. So it's quite a bit more energy, even though it might not look like it, between the black and the blue, if you charge your battery at a low rate, meaning low power. However, you can also see that for the black one, the thinner electrode layers, you can run them at much higher powers to get the same amount of energy out of that system, or put the energy in during charging, versus the blue one that fails at much lower charging rates or power. And that has to do with how quickly these lithium ions can travel through your battery, right? Through the porosity that's between your materials. So if you look at it in somewhat of a visual way, if you have a thin battery, just look, think the current collectors are right here, you build up a concentration gradient while you're charging your battery from the cathode to the anode. The anode is the one in charging that takes up the lithium ions, so they get depleted from that pore space, from the electrolyte during charging. If you make these layers thicker and thicker, you get to a gradient where you might reach a concentration of lithium ions of 0. Somewhere close to your current collector. And at that point, you have to stop charging, otherwise your potentials go haywire and you start plating lithium and things like that. So your voltage really gets out of bounds once this happens, so we can't really go beyond that point. We have to let the lithium ions re-equilibrate, or just be slower so they can replenish the lithiums that have been depleted. Now there's been some work of this. Very simply, conceptually, of course, is the more pores we have, the quicker the ions can move, the more ions there actually are in the electrolyte, because you have more volume of your electrolyte, so you can get better charging rates or power. At the same time, the more pores you put into the system, the less energy you can store. So that's not necessarily a good idea. So the low density, low energy density, power density, however you want to frame it, is a problem. And there's a bit of math you can do. This is one example that I like, which defines the diffusion limited C rate. So the C rate, or charging rate, is how we classify in batteries how quickly we're trying to charge or discharge the battery. It's relative to how much energy the battery can hold in the ideal case, let's say when you charge it very slowly, right? And C rate is inversely proportional to time. So a C rate of 1 means I'm trying to charge my battery in 1 hour. It's based on hours. A C rate of 10 means I try to charge my battery in a 1/10 of an hour, so 6 minutes, very fast. A C rate of 0.1, or 1/10, means I'm trying to charge my battery over 10 hours. That's pretty slow for batteries, so 0.1 C is usually kind of our baseline. That's where we don't have issues with that mass transfer. 1 C, 2 C, 3 C, that's where we get really fast, right, sub-hour charging, where we're interested in. And what this equation essentially shows is that, of course, the diffusion coefficient of lithium, how fast it can move through the electrolyte, matters. The faster it can go, the faster you can charge your battery. The concentration of lithium ions in your electrolyte is important, though that's limited often by solubility, and has sometimes at the very high concentrations a negative effect on the diffusivity. There's the thickness of your battery here, right? That's what we have seen here. The thicker your battery, the slower you have to charge it. And then there is the porosity here. That makes sense. We mentioned that before. But there's also this gamma factor here as an exponent. That's what's called the tortuosity factor. That's essentially describing as like how tortuous is the path to get from one side to the other. Because even though if our distance or thickness of the battery is 100 micrometers, the lithium ions might have to travel 300 micrometers in real path. And if you've ever walked around Boston or driven around Boston, that's exactly what you have. I want to get over there, but I have to go around 10 miles to avoid all the one-way streets, right? That's essentially your tortuosity. So these are handles we can deal with. Porosity, we don't want to increase too much because then we lose energy. Tortuosity, on the other hand, is just how do we architect that porosity. And that's something we're looking at, specifically looking at these straight channels that go from one side to the other of the battery, because those straight channels is a tortuosity of 1, right? And we can have these, again, go from anode to cathode. We're even thinking of ways, well, can we even architect the porosity within then the walls that surround those highway channels to increase ion transfer even further. Now, if we look at this equation here and we put some numbers to it that are typical, again, tortuosity factors from straight, meaning 1 to 8, 9, or 10, which is often reported for just random particle agglomerates, and we look at different thicknesses. So here we're plotting it for a thickness of 200 microns, which would be a fairly thick electrodes, not what you have in your batteries or cars these days. And we look at different porosities listed here from 23%, which is a very low porosity. That's what we often have in high-energy batteries, up to like 50 and above %. You barely see that ever. It's too much porosity, but we can plot it. So over 200 microns, you can see here that even at a moderate tortuosity, you're limited often to C rates, meaning how fast you can charge it, to 1, meaning an hour or slower, right? But you can also see that by changing your tortuosity, let's say for 1 porosity, you can actually double or almost triple that C rate, going from a tortuosity of 6 to a tortuosity of 1 or so. So tortuosity is really something that seems important, especially if we're thinking about, well, how fast do we really need to charge our battery? 5 minutes might be fast enough, right? That would be C rate of 12. So that would be a good target. But here we're not even getting beyond 2 when we make such thick electrodes. Now we also look in our hypothetical architecture here at, well, these walls, let's say they're 10 or 20 microns thick, right? So if we just look at 10 or 20 microns, how does the picture look here? Well, now we're getting to C rates really almost independently of porosity, so 18, 24%, we're getting C rates of 60. So this seems to indicate that, well, if you're getting down to 10 or 20 micrometers, right, a C rate of 60 would be a 1-minute charge. Everyone would be happy. So it sounds like, right, these very thin layers, if it was a thin layer as a single layer in your battery, would be really fast, but you wouldn't store much energy. But if we architect it like that, the thin layer may not matter as much. It's really just the electrode level, the 100 to 200 micrometer thickness that we have to worry about. Now, this is an equation that has some backing to it, but it may not necessarily directly correlate to what we observe experimentally, and I'll show you that later as well. In any case, when we look at that, right, the questions we should ask is, okay, what's the right balance of low tortuosity pores, let's say these channels that we architected here? What about the porosity within the wall? Can we push these together, make like 5% porosity, and we're good to go? And how does that correlate to the electrode thickness? When you ask a question like that, it's a terrible question unless you actually detail it out a little bit, because there's not one perfect architecture here, right? The question has to be, what's the right balance for the specific application or the specific specifications that you need? And oftentimes we think about energy requirement. So how much energy does a kilogram of my battery have to hold? And then ideally, we want to have that energy at the highest power or charging rate possible. That's really one way you can think about this, right? But it has to be there. There is no ideal battery architecture. Now, this looks like something that should be cool to model, right? Especially our straight channels, pretty straightforward. But I do want to emphasize the multi-scale aspect of this problem, right? We have these particles that are usually a few hundreds of nanometers. The interparticle pore space is tens to hundreds of nanometers. We have these channels, let's say we put them into the micrometers, 1 to 10 to 20 micrometers or so in diameter. And then the electrode thickness is on the level of 100 micrometer plus, right? So we're spanning orders and orders of magnitude in scale, which for simulations can get a little tricky here and there if you're trying to resolve all the important resistances, mass transfer limitations, et cetera. So data science or some kind of AI-enabled combination would, of course, really help there. Data science, as I understand, I'm an experimentalist, needs really well-labeled data. Right? Good data sets, and not just that, it also needs a lot of that. And you'll see that actually making a bunch of different battery architectures and measuring them in different ways, we have questions like, well, what is the data you actually need? And how much really can we produce? Because making and measuring batteries is a fairly slow process, right? So how, and this is something for you all to think about, right? It's like, how can we take some of the experiments I'm going to show, or techniques, as well as what you might find in literature and other people are doing, combine it with modeling, and all together in an AI model or so to get the answers that we would like to have, which we really don't have at the moment. Now, getting to the experiments, so when we looked at this concept of we want these low tortuosity channels that are going vertically through our electrode, I have a polymer background, so I was thinking of these phase inversion membranes. This is a cross-section of a water filtration membrane that has these channels from a very simple process, which I'll show you in a second. Right? These channels are cylindrical. They go straight through the cross-section. They can be graded or single diameter. We can tune that. But it's a very simple process, and we set out to think about, can we tune that process so we can tailor all these different architectural things and then just measure their battery behavior, see how they correlate. So how does this process work? It's incredibly simple. You all could learn in it like 5 minutes, at least the basics of it. You take a polymer solution, right, a liquid, you spread it onto a substrate, like putting paint on the wall. And then what we do is we make use of the fact that the polymer solution and the polymer itself might have liquids that it doesn't like. We call those non-solvents, which cause this polymer to precipitate. So we take our wet paint on our substrate and immerse it into a non-solvent. That's often water. Most polymers don't like water. Now, if you're using a solvent that by itself is miscible with water, but the polymer wants to precipitate, you get this phase separation. So this is the ternary phase diagram of the 3 components. You quench the overall system into a space where it's thermodynamically unstable. So you're causing phase separation, and that phase separation is between the non-solvent, often the water, as droplets inside that matrix of now a very high polymer concentration, gel and later solid, the more of the solvent it drains out. Now that all happens at the interface between the 2 liquids, and it grows away from these interfaces. That's how we get these high aspect ratio pores in a very simple process. We literally just paint and dunk, and the rest is happening by soft matter phase behavior that we try to control, but we don't have to individually write it. And you end up with these films. It's really straightforward. It's done roll to roll on an industrial scale for filtration membranes. Now, we adapted this process and made battery electrodes. So this battery electrode here is an electron microscope image of the cross-section here and the top surface here. So it kind of looks at 45 degrees angle here. You see these channels. You see these channel openings on one side. That's a freestanding electrode we made with that process. 80 to 90% of our charge storing material, and the rest is typically some carbon that we carbonize from the polymer to give it electronic conductivity. That's how we currently do it, and we get these electrodes. And we tested these, especially with materials like lithium titanate and lithium phosphate, because they're very stable chemically, so we can really hone in on what is going on with the structure, rather than having to think about the chemical stability of the material. So we like to use lithium titanate as an anode material, lithium iron phosphate as a cathode material, because they're chemically very stable. And we've shown that we can cycle these for 1,000 cycles and you know, keep 80% of our capacity, which is really a benchmark that you want to hit, and these materials are fine, and the structures are fine, most importantly. Now, if we look at our electrodes, right, we want to modify these structural parameters, how thick the electrode is, how big the channels are in diameter, and if there's a gradient or not, how many of these channels are there, and again, what's in the wall, especially the porosity of the wall. And we realized that a lot of the process parameter of this really easy polymer processing fabrication method impact all of these things, right? And we really experimentally over the last 5 years have figured out a lot of these things. I won't bore you with all of them because I want to show you some battery data, but really the most important one are, of course, that we can make them thicker or thinner, so we can change the electrode thickness or height. We found that the non-solvent, that immersion bath, has a very strong impact on how many of these channels we have, so we can go from hundreds and hundreds of these channels per square millimeter down to a few tenths. So a couple orders of magnitude we typically can tune, and of course we can get 0 if we want to. And we found something that wasn't really established is the question of how can you tune the porosity within these walls, and we found that how long you leave it in the bath really impacts that, where we can go from essentially no porosity within these walls to very porous walls fairly seamlessly. Now, I got to skip ahead a little bit, but we started looking at a few of these electrodes, and these are 6 different distinct architectures. We looked at 18 in total for this particular system, which for us is a lot. For the battery field, having 18 distinct architectures of an electrode that's compositionally the same is a lot. I know when I talk to data and people, I was like, 18? Can you like put a couple zeros on that, and so we can do with that? But that's really what we have to work with, right? We're pretty happy that we can do a lot of these tunings here of different channel densities, right? That's what we show here, of different wall porosities, which impacts together with the channels how much total porosity we have, right? The porosity in these different electrodes is just shuffled a little different between the channels and the interparticle porosity. And we can look at what the effect is. So the way we classified these was essentially looking always at 2 electrodes that have approximately similar porosity, like between 30 and 40% overall, but one of them has no channels in this case, and one of them has 200 channels per square millimeter. And we find now, again, on the x-axis here is for different C rates, when we charge it very slow over 10 hours, we get full capacity. And then if we go to something like 2C, which is a 30-minute charge, for one of them, we essentially only can put 10% of the capacity in. For the other one, we can put 50% in. And that other one is the one that has the channels with overall similar porosity. So the channels really seem to do something for these fairly thick electrodes. These electrodes on the order of 200 micrometers, which is around 3 times thicker than what you currently have in your electrode. We can look at the high porosity end. We see very similar things, but of course, because they have higher porosities, they work well, either of them, low channels, high channels, until you get to the really high rates, like 15-minute charging. And I really like to focus in on this middle one because we were able to make 2 electrodes here that have almost the identical total porosity, 43 and 45%, but one was 30 channels per square millimeter, the other one was 160 channels per square millimeter. And we see that at a 1C, so 1 hour charge, they pretty much behave very similar, 80 to 90% capacity we can get. And then we accelerate it to twice that rate. One goes below 40%, the other one stays at 80%, right? So just from 30 to 160 micrometers, channels per millimeter makes such a big difference. And I want to emphasize here that the difference is really just, is the porosity in these channels, or do you have porosity in the interparticle space, in the walls we call them, right? Because the overall porosity is the same here. So the channels can really, like, contributing some of the porosity into the channels can really make quite a difference. Now, if we look at this, this is just really the blank capacity that we get out of these electrodes at different rates, and we usually do it 4 or 5 times per rate to make sure they're stable at that rate. Right? There's other measurements we do, like electrochemical impedance spectroscopy, which tells us a little bit about the resistance that our system has. And interestingly enough, when we do that, it's a very common analysis method in batteries and electrochemical systems. We find that the resistance of the one with very few channels, so more porosity in the wall, is much lower than the resistance that has a lot of channels but has a very dense wall, which is the opposite of what you see in the cycling data. So the resistance measurement itself doesn't really tell us a lot. In fact, looking through all our data, this resistance measurements, which is an AC impedance measurement seems to really just probe that local environment around the particles. It doesn't probe the electrode level over tens and hundreds of microns, which is really the relevant length scale that we care about to a big part when we charge full batteries. Now we can also look at, this is the raw data when you actually charge or discharge. In this case, we lithiate a battery, where we apply a constant current, and we measure the voltage. And with this lithium titanate, what you usually see is this flat plateau until at some capacity, or that's a time axis as well at constant current, it just falls off because now you put all your lithium into the material, you're done with the chemical reaction. The faster you do that, it always happens that you can put less and less lithium in it because the lithium doesn't have time to find all these particles essentially to meet them. But you can also look at this distance in plateau here versus what it should be at around 1.5 volt. That's your overpotential, which is really coming from ohmic resistances, but also from depletion effects of the lithium ions. So there's a lot hidden in this data here that we often don't look at because this is kind of our standard performance data, which really just gives us the endpoint, right? But between these kind of things, we can ask, well, what is actually the data that matters? What is the one we should, import, for example, into an AI model? What's the data that we should simulate if we couple experiments with simulation to get bigger data sets, right? So these are things we have to think about. We started doing some other data gathering too, in particular relaxation data, where we charge our battery at a high rate for just 10 minutes or so, and then we watch the voltage at open circuit relax back to its thermodynamic equilibrium. And how fast that happens seems to correlate really nicely with exactly how well they perform, right? That relaxation has a lot to do with ion distribution diffusing around in your electrode. So we didn't just randomly do this. We thought, it's like, you know what, relaxation after we really polarize our battery should be related to the performance that we see when we charge and discharges, and it is true. So this is an interesting type of data, that might help us classify certain things or connect physical processes to data as well. So something to think about. Now, I'm running a bit out of time, so I'm going to skip over a couple things. I do want to note that we started, so far I've pretty much only been talking about shuffling porosity between the walls and these channels. More channels and less porosity in the wall, or more porosity in the wall and less channels to kind of keep the overall porosity the same. We also realized, though, that the architecture of that porosity in the wall seems to really matter too, specifically the connectivity. We can have walls that have a bunch of pores, but if these pores are closed off, they're not really helping the ions to get through that porosity, right? Think of a closed pore sponge or so. So we found with some polymer engineering using polymer blends or blockopolymers, where one of them forms our carbonaceous matrix that keeps our particles together, the other one forms pores. We can actually create more connected sub-micrometer or nanometer porosity that seems to really improve our rate capability. So on the left side here, I pulled up again our medium porosity electrodes from earlier with more or less channels. And on the right side now, we added a little bit of this second polymer here that creates this interconnected porosity. And we find that we can, A, increase the number of channels while keeping the overall porosities pretty similar, here 45 versus 47%. But now if you look at this data point here, this is a 15-minute charge, and we can achieve almost 60% of the capacity, while here at a 15-minute charge, we essentially crapped out. So we shuffled more of our porosity around, but we did more than that. We somehow managed to change the connectivity of the porosity in the walls, which if you remember my SEM images from earlier, we have no way of really quantifying that. Right? The resolution of that is in the tens, maybe a couple hundred nanometers, but it's a very mixed composite. So quantification of that connectivity of these, this pore space is very difficult, and we don't really know yet how to do it, but we see the impact that it has. Now I'm going to leave it at that. I'm just going to mention that at the end, you also always have to think about, do you care about mass of your system? Do you care about volume of your system? Do you care about capacity, which gives you a driving range? Or do you care about, there should be energy somewhere here. This is an energy plot. Energy is capacity times the voltage, right? If you charge your car very quickly, do you just want to make sure you can, after 10 minutes, drive another 400 miles? Or do you care that you had to spend an extra 30% on the energy cost because you just had a lot of resistive losses? You may not care, and you may only care about speed, but those are considerations you have to make. I hope I convinced you, though, that the general way we make these electrodes, we actually get quite a bit of tunability, even though we don't know yet how to characterize all of the structural aspects. And that might be a good complementary platform, together with simulations, to start building some more multi-scale interconnected models that explain some of the data, but also then hopefully predict, hey, this is the type of architecture you should be trying to make if this is the kind of performance you're looking for. There's the energy. So I'll just leave you with a bunch of pretty pictures and happy to answer any questions. Thank you. And I have one. Do you want this one?
Thanks, Joerg. So I didn't really understand how this very simple process that you outlined for making these electrodes can be controlled to, for example, influence the porosity or the connectivity in the walls of these things. How do you do that, right?
So that's, in fact, exactly what's shown here. So I'm just going to zoom right in there. So we found that it is how long this polymer that has a bunch of particles with it and solidifies once we put it into the non-solvent bath. So, nope. It happens in that step where these channels form. That happens within 10 to 20 seconds. What happens afterwards is shown on the right in the schematic. More and more solvent gets drained out of these polymer particle walls. There's a lot of that trapped in there. It's like a gel. And the longer we leave it in there, the more solvent we remove by extraction. And this can take hours. So we have a nice time frame after we put it in the cylinder's form where we can tune that porosity. Because the step after that is we dry it. So the more solvent there is in our gel when we dry it, the more it compacts. So if we take it out after a few minutes and dry it, it really shrinks down and compacts those walls, getting rid of all that porosity. If we leave it in there for hours, all the solvent is extracted out. Now it dries as a very porous, almost aerogel or solvogel in that sense. So that's how we found we can tune over quite a bit of a margin that wall porosity, which was really important for us because the channels did their thing, but it's not all of it.
Well, please give Professor Werner another hand. It is my pleasure to also introduce Professor Boris Kozinsky. Professor Kozinsky is a professor at Harvard University with appointments in materials science, mechanical engineering, and chemistry. He did his PhD at MIT, and following his PhD, founded the Bosch Research and Technology Center in Cambridge, where he remains as the principal scientist leading the direction of materials simulation and discovery. His research group focuses on developing advanced computational methods to accelerate the discovery of materials for energy applications, such as batteries and catalysts. Please join me in welcoming Professor Kozinsky.
Great to be here. The view is fantastic. I'm going to enjoy this. All right, so let me just fire up my slides. Oh, perfect, it's working. All right, so I'm going to tell you a little bit about how we can use computers for understanding and designing materials. I'll give you a couple of snapshots of what we are currently working on. And to start off, just to remind everybody that our civilization is kind of labeled by the materials that we use. So materials are kind of important, and currently we are in the computer age of materials, which means we can actually maybe use computers for this. And if you ask what kind of data do we have, why can't our computers predict materials for us already? Like, you know, if I asked my favorite LLM to invent a new material, it actually will give a funny answer and not actually do anything useful. And the reason really is not because those LLMs are stupid, they just don't have the data, right? So if you look at what data we have in materials, what do we know about material science? It's really little, because materials is not really a very well-defined thing. Material could be very complicated and have very difficult nuances to look at. And so we have very fragmented data that exists in various types of materials and the various properties, and the combinations of properties and types of materials is so large that we don't have anything right now that's available for training models yet. So that's the goal, right? So we want to generate that data, and experimentally, of course, it's very difficult. So we want to use the basic physics to do it, so computational techniques based on quantum mechanics. This is, of course, based on the Schrödinger equation, and we can try to solve Schrödinger equation for simple systems like atoms, and everything is made out of atoms, so we can make nice simulations of small molecules and be quite accurate in comparison with experiment. These first principles calculations are very, very encouraging in their ability, but they are a bit slow because they require a lot of computational resources. Suppose you have a very large computational cluster available, then you can imagine doing systematic calculations of properties of materials using these quantum mechanical methods from many different types of materials. And of course, the vision is you can screen lots of materials to find something new that has not been found yet based on these predictive first principles quantum-based calculations. And this is, I want to just show you some examples to show that this is not just a fantasy. This has actually a chance of success. The first example, very quickly, I'll show you on thermoelectric materials, which are materials for converting energy from thermal to electrical. In other words, you have a thermal gradient of some sort. You can convert it to useful electrical energy and put it even in a car to harvest some of the heat in an exhaust pipe. And these are materials that are actually used to power all the space and Mars missions. And what you need to do to actually calculate the efficiency of this conversion is look at the Seebeck coefficient, which measures how good the material is at converting temperature gradients to voltage gradients, and conductivities of electrons, and conductivity of heat in general. So this is something that you don't want to have too much of, because you want the temperature gradient to stay high, and you want those electrons to come out easily, so you want the electrical conductivity, and you want the Seebeck coefficient also to be high. So predicting these quantities is difficult. So you can do it from first principles. It does require method development because you need to calculate not only band structure of your materials, which tell you the levels of electrons. You also need to calculate how these electrons relax. In other words, how they scatter off of other things. In other words, to calculate resistivity, you need the resistance mechanisms. And so this is the difficult part, is to compute this from first principles. You need to account for all possible ways you can scatter a traveling electron off of atoms, off of other electrons maybe, and that requires a lot of computation. And the point here is that you have to still develop methods for each property like this to be able to do predictive materials design. And this is an example of that story, is you can implement computational codes that are efficient at predicting scattering mechanisms and lifetimes of phonons that carry heat and electrons that carry both heat and charge in your material, and predict conductivities, use those conductivities to assess how good a thermoelectric material is that you're trying to compute. So if you have this machinery, you first have to validate against very careful experiments, and these are measurements on graphene versus the predictions from theoretical calculations, and these are scuderites, a more complicated thermoelectric crystal, where also this is experiment and theory together. So you can actually be very predictive and accurate at some significant computational cost, but nonetheless, you have an ability now to do a digital twin kind of analysis of a thermoelectric material, and then you can use it to screen materials. So now you can go and do hundreds of compositions, and for each one, compute property, and for each property, change the doping level of the material and optimize that property. And you can even invent new materials this way. In other words, look at compositions that have not been made before, like this one here and this one here. These didn't even exist, but you can make them on the computer very easily by just putting atoms together, predict the property, and then try to be very convincing with your experimental partners to try to make them. And that takes a lot of experiments with arc melting and all sorts of things to get these done. But once you do them, you can actually end up with record high temperature performing materials that have not been even known to exist before. And you get these thermoelectric materials essentially designed. This is a slide I like to show to industry. You get this kind of improvement in performance and drop in cost in a fraction of the time that it used to take when you do a trial and error way, the old style, by just sort of randomly mixing powders together. So you can get a better material that is 10 times cheaper, and you get it 10 times faster. So this can be done. This is an example of the feasibility, but it's still very difficult because it requires method development. And that's what our group mostly does these days. Of course, we want to do it for catalysis. We want to do it for batteries. We want to do it for drugs and many other applications because it is possible. It just requires a little bit of work. Okay, so the story always starts with electronic structure and quantum mechanics. From that, you can calculate how atoms move around. And this is important for all sorts of reactions. And if you can understand these reactions and accelerate them on your computer, then you can answer how a material is going to evolve, how it's going to react to chemical and environmental stimuli, and then get to sort of a realistic model all the way from quantum mechanics sort of ground up like this, right? So that requires acceleration of every step and compression of information because it's just intractable to go from many-body Schrödinger equation all the way to a large-scale structure simulation like this. So the way we think about it is, well, we have this hierarchy of methods on a computer. Here are all the very expensive wave function quantum mechanical methods. We can afford to do them for like 10 atoms or something like that. We have density functional theory, which is the most popular computational method ever. Like 40% of all computing power in the world in these academic supercomputers goes to computing DFT for materials. So it is faster, but it still has its issues because we cannot do anything more than 1,000 atoms realistically. So we try to use machine learning for bridging the scales. In other words, compressing information from accurate slow method into faster surrogate methods, and hopefully not losing too much accuracy. And so we do this for learning how atoms interact by essentially coming up with models for this interatomic energy or potential energy surface, starting from quantum mechanics and then mapping only to the function of atomic positions. And then we also try to make better approximations for the DFT itself for this method, starting with a slower and more accurate wave function method. So this is basically a way of compressing information, and then you can chain these together to get better, faster models at higher accuracy. So in molecular dynamics, this is a method that we actually use to move atoms on computers. We need to compute forces on atoms that come from the energy of the interactions between these atoms. And we can do this with quantum mechanics, which is slow, as I mentioned, and we can do this with machine learning, which is trained on quantum mechanical data to be faster. And so this has been quite important in our field. And what we have done is invent new types of machine learning architectures that are better than previous architectures at learning this task. In other words, you give the model a structure of a molecule or a material, and you ask that model to predict the energy, and you can take that energy and differentiate it with respect to positions to get forces, and you can use those forces to run your molecular dynamics simulations, just following Newton's equations. And so this is a difficult task to learn atomic interactions from quantum mechanics and not have to deal with electrons. You are asking the machine learning model to learn all of quantum mechanics somehow. And so these models need to be big, and they need to be able to learn all that, right? So we developed these architectures that encode as much as possible geometric information because you move atoms around, the ground state of electrons changes, and you need to learn that because that determines the energy. So our models have this ability to understand where the atoms are in space by tracking their distances and orientations of the bonds and sort of all the directional information. We call these equivariant machine learning models that have some interesting mathematical properties that, the features that these models learn, like these are deep neural networks, these features are not numbers. They are vectors and tensors and basic geometric objects that rotate together with the structure that you're studying. So that means that the models know how to predict correct energies and forces respecting our physical symmetries. In other words, they preserve angular momentum and linear momentum and energy, all of that nice stuff, and they also are general. So this is basically reflected in their ability to learn faster than models that don't do this, and this is just an early example showing that if you do machine learning, you always track the training error as a function of your training data, training set size. These equivariant models have a different scaling exponent, which is very unusual in machine learning, that you have a model that learns faster by a power law as a function of the number of data points you feed it. And that is very beneficial because you need, for instance, 1,000 times less data points to learn a certain material potential energy than previous models, and you actually get a much lower error. So this is now enabling you to do essentially approximations to quantum mechanics at not so much computational cost to get that quantum mechanical data. You can get away with a few hundred structures, and that's quite useful. And there's many variations on this theme nowadays. So the ecosystem of machine learning potentials, if you follow that field, is composed of ideas that are very similar under the hood with some minor variations and different implementations and different efficiencies. But all of them are these message passing neural networks that share information between atoms that are tensors encoding geometry, and then they learn energy as a function of atomic positions. And so all of these models now are able to simulate pretty much any material that you can get your quantum training data on. So this is one example of one of these models that we just wanted to show that these are not necessarily slow and impossible to use for real applications just because these are big neural networks. You can actually make implementations efficient, and this is something that we're working with NVIDIA on, and other companies are paying a lot of attention, and they're using these models because it's now possible to parallelize these calculations on many GPUs. If you're lucky to have so many GPUs, you can run a simulation of a blood clotting protein explicitly solvated in water, for instance. In this case, it's at quantum mechanical hybrid level accuracy, and this is one of the machine learning models that is running the dynamics here. And yeah, students like it because they can submit to all sorts of awards, these kind of movies. What's happening recently in the field is that while these models have been able to learn pretty well each individual material, why can't we have these models learn many materials or all materials at the same time? This suggestion has been, why don't we take one of these models, make it very big, and try to learn all of quantum mechanics for all material compositions? And this is an interesting exercise. Of course, it's not going to give you an accurate model for any given material, but it's interesting to see how far you can push this to learn all of a ground state variety. So this is what has been happening in last 2-3 years is people have taken all the available quantum mechanical data, and some companies have even generated massive amounts, hundreds of millions of DFT calculations, and now there are efforts in taking these large equivariant models and training them on all of the available data and seeing how well they can be used for pretty much computing any known material. And this is sort of a competition in the field where people, as soon as they have a new model or they train a bigger one because they have more resources, they would put it up and say, we have the leading model now. Well, this is now outdated, but they're basically this sort of benchmarks, which are actually quite nice for driving the field forward because people develop new things when they compete. Anyhow, these are models that are very large and rather slow, so you wouldn't necessarily use them for big, fast simulations, but they have a lot of knowledge already encoded in their latent sort of representations that you can use them for fine-tuning on specific materials that you may be interested in and maybe even distilling them. And we're thinking about this a little bit further. Remember, it's sort of we're after material properties in general, so just computing energies is nice, but it's not the whole story. You may want to predict responses of materials. So this is an example of using some of these models to predict responses to electric fields. So this is in ferroelectric material domain, where this is barium titanate. We can actually do a simulation that takes a large representation of this material and applies a sinusoidal electric field and looks at the hysteresis of the polarization switching. Let me just play this movie here. So you can actually see how domains in the ferroelectric nucleate, how they grow, how the switching can happen. So you can maybe simulate a ferroelectric semiconductor device or something like that on the scale of maybe a few million atoms, and predict coercivity and look at frequency and temperature dependence of these things. So these are kind of like now simulations you can perform essentially at quantum accuracy for realistic materials that you might want to make devices out of. And yeah, so one bottleneck, of course, is that you need training data, as I mentioned, right? So the training data can come from these databases that have pretty much a little bit of every crystal, a little bit of every molecule. But when you're dealing with reactive systems, this is really insufficient because in reactive systems, very rare specific phenomena drive the whole performance of material, and you don't know them ahead of time, these mechanisms. So it's nice to have models that can automatically say, well, you're asking me to predict something I have not been trained on, right? A normal scientist would hopefully do that. Try not to answer questions they are not experts on. And so models can only do this if they know what they don't know, right? So if you have some sort of a way of building in uncertainty quantification into the models, then you can have that kind of capability. Unfortunately, neural networks are not like that. Like any chatbot will answer any question, but won't tell you how confident or correct it is. So this requires a different type of machine learning models. And we rely for this problem on Gaussian process regression, which is an example of Bayesian inference, where you predict not only the mean of what you think is the prediction of all possible sort of realizations of your model, but you also predict the variance, in other words, the uncertainty of the, so you predict the distribution of answers. And the width of that distribution tells you how confident it is, and it will be narrower if you're close to the training data, and it will be wider if you're far away from the training data that you've seen. And if you have that ability, then the model can stop and say, well, actually, I need more training data. Let me call my quantum calculation, and then I'll get back to you, right? So this is an active learning loop that you can implement to autonomously train the model, and it basically asks for data as it goes on its own. And this is a kind of technology that's enabling for studying reactive systems where you don't know what training data you may need ahead of time because you haven't seen what the material might do. And this is what we need for catalysis, right? So in catalysis, there are these reaction events that happen on surfaces, and the structures can be complicated and mechanisms are very poorly understood because they're invisible to experimental characterization. You only see the long-lived states. You don't see the intermediate reaction steps. And so this is an example of hydrogen reacting with platinum catalyst. And this model was essentially started with no knowledge. The Gaussian process model here has zero knowledge to begin with, so that's why you see in the beginning it does a lot of these requests to call DFT, so it automatically calls a quantum mechanical calculation, gets training data, and then proceeds afterwards. And then once it's done, you can actually test how good it is and compare to experiment. For instance, you can measure the activation energy because you can now run larger reactions and measure how many molecules reacted as a function of time, and then change the temperature of the simulation and compare to what experiments do exactly the same way as they measure reactivity as a function of temperature to get your activation energy. And then you can do more complicated things like start playing with alloys and ask what are the active sites, what is actually catalyst doing, like on which site does the molecule adsorb, change into a different molecule, does it move around the surface? And so we can sort of decompose our simulation now that it has seen all the data and actually has all the events there. We can establish its correctness by comparing to experiment macroscopically, but then also ask it to look at individual atoms and molecules and figure out what the mechanisms are. And so we can find out that, for instance, individual palladium atoms are the sites responsible for recombining and desorbing molecules, And islands of palladium are the sites that are responsible for absorbing and dissociating molecules. So you can sort of get this whole reshuffling of the chemicals. And you can also ask, what happens when you take this material and you have it in a chemical reactor for a long time? How does it degrade? And you can find out that these active sites actually disappear in a certain way, and you have this reactivity that basically shuts down above a certain temperature, and that tells you what to do to a material to make it more robust to temperature cycling in actual chemical reactors. So these are kind of like these digital twin of catalysts now that you can use. Okay, so I did want to include an example of batteries, just because this previous talk was on batteries, so I put in a couple of slides here on interfaces that are responsible for degradation in solid-state batteries, or in any battery. Actually, you have these certain phases that grow in when electrodes and electrolytes meet and try to sort of live together. They actually react over time. Some reactions are very fast. So this is an example of a simulation of a degradation reaction in a solid-state battery that has a very fast electrolyte, very fast ion conductor, a solid-state sulfide, and lithium metal, which is one of the good candidates for the electrodes. And you can see in the simulation, again, this is a molecular dynamics simulation trained on DFT data. You can run it at essentially this kind of representative geometry of a battery, and see that there's a very fast degradation reaction that consumes both the electrode and the electrolyte, forms additional phases which we didn't expect actually. And so this is one of those examples where you learn from the simulation what the mechanisms are, and then you see formation of something that is a product which may not be a good thing because the battery will not conduct ions anymore. And you can do this calculation and then afterwards analyze what actually happened. Like, your electrolyte got consumed, your lithium electrode got consumed, and you have these additional phases that started growing very rapidly, even at room temperature, in about 50 nanoseconds. There's this sort of thick layer of junk that you don't want, but you actually understand what it is, hopefully better. Okay, so very quickly, maybe in a few minutes that are left, I want to tell you what the major issue is, right? It all sounds nice. These movies are great, but they are only as accurate as the quantum data that you train them on. And the quantum data that we have, unfortunately, is not very accurate, despite the fact that, it is derived from the Schrödinger equation. There are approximations along the way that are very crude. So in other words, we cannot do very predictive simulations. It's one of the main obstacles in materials design these days, is that these models, these DFT models that I talked about that are very widely used, they're just not good, right? So this is a problem. So as a result, if you try to predict for certain molecules, for many molecules, absorption energies on metal surfaces, you can be off by a very large amount, like 0.6 electron volts. If you predict voltages of batteries without any empirical corrections, so from first principles as much as you can, you're also going to be off by maybe half an electron volt. And this is because of the way that these approximations are made. And so we're revisiting this problem again in this kind of way from higher order, more expensive methods. We're trying to machine learn the correct approximation without having to make human intuitive choices. And so these models are now operating on the level of electrons. They're trying to learn the many-body quantum mechanics and to map it onto simpler one-electron quantum mechanics in sort of in an average way that we can then use for much faster simulations. And I'll skip through the technical details just to say that these are also either Gaussian process regression or neural network machine learning models that are trained on more accurate data that we can get from even experiments that are very careful, or from some more heavy calculations. And just to show you examples of how well they do, well, you can actually get nowadays, these are some of the recent results of these models, being able to predict band gaps and charge transition levels of defects in much better agreement with experiment than previous generation models that are have been used for decades. So semi-local functionals, if you're in this field, will not predict very accurate band gaps, of course, and electron levels. But these CIDR models, these machine learning models, can do much better at essentially a similar cost computationally to what previous models we're doing. So now you can go up to, let's say, 1,000 atom calculations while keeping full hybrid accuracy. You can look at defects like zero phonon lines, or basically properties of defects in excited states and materials that are important for quantum computers. Again, that requires large simulations because these are defects in a crystal, so you need to simulate a lot of the crystal around the defects to answer questions about, like, what do the electrons do when you shine light on them and things like that. So you get much better agreement with experiment for these kind of NV centers in diamonds and vacancies in silicon carbide compared to previous methods, and even sort of state-of-the-art hybrid methods, which are very expensive to do large calculations with. You can look at polarons for all sorts of photovoltaic applications as well. And electrons are much better behaved when you introduce these machine learning models in comparison to previous generation models. And I'll just want to maybe show you one last slide. Now, in application to catalysis, this is one of those pain points I mentioned. That absorption energies are very difficult to describe accurately. These are examples of very sort of recent computational attempts to compute adsorption energies of these carbon monoxide molecules on metallic surfaces, specifically on platinum and rhodium and all these kind of things that are problematic. And we can finally get adsorption energies in close agreement with experiment at the same time as bulk properties of the actual metal, and also capture the correct site on which molecules would absorb. So these are known experimentally, but they're impossible to get with any DFT calculation, with any combination of functionals until now. So, but now these machine learning models are showing promise that we can actually do this if we do a lot of training on many-body quantum mechanics. Okay, so with that, I'd like to thank you for your attention and happy to answer any questions. Of course, thank you to all the students who've done all the work. Thanks.
I have a question. So your model, it bakes equivariance into the architecture itself. But there's been like an increasing body of work that shows that models which aren't enforcing these constraints, but rather which learn equivariance from the data itself, are unsurprisingly more efficient, but also somewhat surprisingly capable of higher accuracy. And so do you think that state-of-the-art models will continue to satisfy equivariant constraints?
I don't know. I mean, this is, I think, still an open question, at least in my mind, whether these models can be fast enough and also can extrapolate well, rather than just learn on average, because, yeah, these unrestricted models in several applications have been seen to learn well if you make them very, very large. So these models that I think you're referring to are much, much larger in the number of parameters than equivariant models. So maybe they can learn. I'm not sure how well they will generalize. This is still an open question. So maybe all of physics can be learned with a large enough neural network. I'm not sure.
Thank you.
First of all, thank you for putting a slide on batteries in there. The combination of the active learning, as you showed it, where it triggers itself, like I don't have enough information here, I have too high uncertainty, I got to do an DFT to get a data point, and then I like that a lot. And when I think about what you showed was the batteries, right? Okay, these are the things that happen there, new structures that might be forming due to the reaction between these materials. Can you now also include an active learning loop that says, like, okay, what do I have to put between these two materials as a interface, like what naturally forms in liquid electrolyte systems, that keeps it very stable over time, which is a coincident there, but can we have active learning loops that predict interfaces for us, for unstable interfaces?
I'm sure you could, yeah. I mean, there's no technical reason why it can't be done. It just hasn't been done. Yeah, but I mean, suggestions of which material combinations to try. The technical sort of issue is still, you know, it's a little bit tedious to set these calculations up because you're now dealing with a new interface. So you need to generate the structure, which currently we always do by hand, but now more and more like these generative models can be helpful in putting together atoms in a reasonable way that we can use to start the simulations. And so this requires a little bit more engineering, I would say, but it's not technically impossible. Yeah.
Thank you for a great talk. So we've heard a lot today about building machine learning models for potential energy surfaces, or for, in particular, the ground state. Is it obvious how to generalize this for photoexcited reactions? So if I really had, and non-adiabatic processes, things like curve crossings and things like that, where you've got lots of surfaces involved, which is a lot of what goes on in most photochemical processes.
Yeah, it's possible, and it's also been done. So by several groups, you could take an excited state potential energy surface and apply the same kind of models to learn it. If you want to study the actual photodynamics, then it's a little bit more complicated, especially when you deal with conical intersections and crossings. You need to also learn the non-adiabatic coupling, which is also learnable. It's not, unfortunately, just a number. You have to learn a vector there, but this is something that we've recently done as well. And you can put together a full dynamics model that sort of captures the excited state as well. So there's somewhat more work to be done there, but the architecture can be the same for both the energy surfaces and the couplings. Yeah.
Boris, a really nice talk. So I just had I wondered about, for some of your surfaces, could you talk a little bit about the training data for these potentials and what kind of systems you train on? And then also, when you're doing the active learning, could you say a little bit more about how you identify, is it some kind of sampling that you use to just check against DFT, or or is it more elaborate? So maybe about the training and the active learning, if you
yeah.
Because I think one thing, the reason I'm asking is that can be expensive, especially if you're training on a lot of surface geometries and things. I could imagine it could be expensive, and you'd want to minimize that computational expense.
Correct. Yeah. That's the whole reason for doing this is to be as data efficient as possible and let the model decide and not us decide. The training data in most applications, we're still starting from a specific structure that we think is relevant for that particular application. And sometimes, like for instance, for the battery example, the training data includes the electrode materials, some representations of the interface, as well as what we think will be the products. And so we begin with that data set. And these are just DFT calculations on specific crystals and maybe molten structures or something like that. We usually generate data at higher temperature than we intend to run them. These foundation models, these very large models, are trained on all of CSD kind of data. That's a bit different exercise there. And the unfortunate thing is that all the training data is at pretty low quality DFT level. And so for many applications, that's also what we start with is some sort of cheap functional. But then when you do active learning, every atomic environment is assigned a certain descriptor, some sort of a vector. And then we have a distance metric, which is a kernel that compares that atomic environment with the environments it has seen in its training set. And then based on that distance, it decides whether this is sufficiently close or too far. And then if it's too far, then the variance will exceed a certain threshold, which we also define a priori by hand, just some number, and it needs some tuning at some point. But if the threshold is exceeded, then the model says, well, it's unfamiliar, and then it will, in that space of that particular material, basically take that structure and run a DFT on that structure. And so it sort of goes on and on and on. So if you show it a very different interface or a very different material, it will definitely say, I haven't seen it before. And then you do have to then do the whole loop again for that, yeah.
Yeah, thank you.
Mm-hmm.
I'm not sure if there's a sort of short answer for this question, but I'm curious if you could comment a bit more on, say, machine learning DFT. And so I guess one way to put this is, I remember DeepMind put out this science paper a couple of years ago, right? And so, using machine learning to improve DFT, satisfying certain constraints. But I haven't really followed that very closely afterwards. And so, but as far as I could tell, the impact of that work is certainly nothing compared to AlphaFold. Right? You could argue, maybe quantum mechanics is more difficult to learn compared to protein folding. But I just wonder if you could comment briefly on where sort of the field is in terms of machine learning DFT. Is it still limited by transferability, between molecules to materials, or between different kind of materials, or where are we?
Yeah. Very good question, and I don't know if there's a good answer for that. I think just very few groups are working on this, and that's the reason why the impact and progress are a bit slow. There's just maybe 3-4 groups are actively pursuing this, and it is challenging technically because first of all, the training data is not there, specifically for periodic systems, where you need high accuracy quantum many-body data, and we just don't have the methods to generate many-body data for solids. We have for molecules, but not for solids, for periodic systems. And so that DM21 paper from Google was on molecular species, and they basically learned a local hybrid, which is a very expensive model to even run, and that's the other challenge. These machine learning models, once you train them, you have to put them inside a self-consistent electronic structure calculation, and if they're numerically unstable, which is a huge challenge for neural networks, and they're heavy, they're not going to be as attractive as what we have currently, right? So you actually make things slower and less stable as opposed to making things faster, right? So, and then you at some point say, well, I might as well just run my quantum chemistry method on a small molecule anyway. So I think that's where the field roughly is that it's very difficult to make a fast machine learning model that is stable. It can run self-consistent calculations, and that's why we don't use neural networks yet. We're trying them, but I mean, the models that I've shown, the CIDR models, are based on manually crafted features that are fed into a Gaussian process regression model, and those features encode certain physics that we think is important, which is much richer than previous approximations. But our main goal is to make them cheap to evaluate, so we can actually do practical stuff like defects and large molecules and things like that. And so it's a very difficult trade-off, getting higher accuracy at the same time as computational efficiency, and also to get the training data. So that's why it's a bit slow.
Please join me in thanking Professor Kozinsky once again.
Thank you.